Hello, welcome. In this short video, let us look at the derivation of CRB in the case where the observations has a noise component that follows a Laplacian distribution. That is, consider the observation x of 0 equal to a plus w of 0, where w of 0 follows a Laplacian distribution defined as 1 by square root of 2 into sigma into exponential of minus square root of 2 by sigma into modulus of w naught. So this is the distribution of the noise component. Now our goal is to determine the CRB for the variance of the estimator A hat, where estimator A hat is trying to determine the value of A. In the previous video, we learned that for a linear model with noise component following an arbitrary probability distribution, CRB is given by integral minus infinity to plus infinity the derivative of the probability distribution P of u whole square divided by P of u du. So this is the CRB. Of course, there is a inverse. So this is the CRB for a linear model with noise component following a arbitrary distribution P of w naught, of course. So here u is equal to a plus w of 0. So the probability density function of u can be determined as follows. The probability of u is less than small u is equal to probability that a plus w of 0 is less than small u, and this is equal to probability of w0 is less than u minus a. Therefore, the probability density of u is equal to the probability density of w naught with w naught replaced by u minus a. And since the probability density of w naught is given by the Laplacian PDF, we have the PDF of u is equal to 1 by square root of 2 into sigma exponential of minus square root of 2 by sigma into modulus of u minus a. So this is the probability density function of the new variable u. Note that this P of u is the probability density function, and this P of u is the probability distribution function or the probability function. And this can also be written as f w of 0 of u minus a, where this f w naught of u minus a is the CDF at u minus a. So this is equal to P of u. This is the PDF, and this is the probability. So now we can use the CRB derived from a previous video. So in order to use this formula, first we need to determine this integral. So the integral is defined as minus infinity to plus infinity derivative with respect to a of the probability density function, that is 1 by square root of 2 into sigma exponential of minus square root of 2 divided by sigma into modulus of u minus a whole square divided by 1 by square root of 2 into sigma exponential of minus square root of 2 divided by sigma into modulus of u minus a du. So this is the denominator in the CRB. Upon simplification, this becomes, now since we have modulus of u minus a, you have to basically break down this integral into two components, that is one from minus infinity to a and another one from a to plus infinity. So since we have modulus of u minus a, there are basically two components to this integral. The first one is from minus infinity to a, and the second one is from plus a to plus infinity. So for the component from minus infinity to a, we basically have u less than a, that is modulus of u minus a is basically equal to minus of u minus a. So by using this condition, we have 1 by 2 times sigma square into the derivative of exponential is still exponential minus square root of 2 by sigma into minus of u minus a. So this becomes plus u minus a. The derivative is minus square root of 2 by sigma whole squared divided by 1 by square root of 2 into sigma exponential of minus plus square root of 2 by sigma into u minus a. For this component, since u is less than a, for this part of the integral. The second component is from a to plus infinity. that is u is greater than a. That means modulus of u minus a is equal to u minus a. In this case, the differentiation becomes 1 by 2 times square root sigma squared multiplied by exponential of minus square root of 2 by sigma into u minus a into square root of 2 by sigma whole squared divided by 1 by square root of 2 into sigma exponential of minus square root of 2 by sigma into u minus a. And of course we have du and du. Square root of 2 by sigma cube into minus infinity to a. Then we have one exponential here and square of exponential and exponential here. So we are left with one exponential, which is exponential of square root of 2 by sigma into u minus a du. And the second term is minus plus a to plus infinity exponential of minus square root of 2 by sigma into u minus a du. Clearly this is equal to square root of 2 by sigma cube. And now by replacing u minus a with v, and the integral limits become, for minus infinity it is still minus infinity, for a it is 0. So this is integral minus infinity to 0 exponential of square root of 2 by sigma into v dv. Now similarly the second term also becomes integral 0 to infinity exponential of minus square root of 2 by sigma into v dv. So square root of 2 divided by sigma cube multiplied by integral minus infinity to plus infinity, since this is equal to minus of modulus of v. This is exponential of minus square root of 2 by sigma into modulus of v dv. That means this is the minus v, that is v is positive for v greater than 0, and v is and clearly this is equal to minus of modulus of v for negative v. So this is the Laplacian PDF. Of course the normalizing constant is missing, so this is actually equal to the inverse of the normalizing constant. So this becomes square root of 2 sigma cube into square root of 2 into sigma, because 1 by square root of 2 into sigma is the normalizing constant for a Laplacian PDF. So the integral of the exponential in the Laplacian PDF should be equal to square root of 2 into sigma. So this is equal to 2 by sigma square. So since the integral in the definition or in the result for CRB is equal to 2 by sigma square, the CRB or the bound on the variance is variance of a hat is bounded by sigma square by 2. Note that for a Gaussian noise, the variance is bounded by sigma square. In this case of Laplacian noise, the variance of the estimator is bounded by sigma square by 2, that is half of the noise variance. Thanks for watching.